The binomial distribution is used when we're dealing with an experiment which is repeated a certain number of times, which satisfies the following conditions. There's a fixed number of trials in this experiment, which we call n. Each trial is independent of the previous. And each of the possible outcomes are mutually exclusive. So for instance, if the experiment consisted of flipping a coin 3 times, well, maybe we would get tails, tails, heads on one flip. Maybe on another flip, we would get heads, heads, tails. Well, those two outcomes are mutually exclusive because if we flip a coin 3 times, we may get one or the other, but it would be impossible to get both of those outcomes simultaneously. So that's mutually exclusive. And finally, very important, each trial in this experiment will have two possible outcomes, either success or failure, meaning to say win or lose, or yes or no, or hit or miss. Two possible outcomes, hence the term binomial distribution. Now, when this occurs, the formula we need to know is the following. The probability of x, that's capital X, being equal to r is equal to the binomial coefficient nr times p raised to the power of r times q raised to the power of n minus r. Now that formula may look a little daunting. You may want to write it down, and we'll start by trying to define each of the things we see here. Now capital X is the discrete random variable. So for instance, if we're flipping a coin, we may want to call capital X the number of tails we obtain when we flip a coin 3 times. So capital X could be 0, 1, 2, or 3, because I could either obtain 0 tails, 1 tails, 2 tails, or 3 tails if I flip a coin 3 times. R is the number of successes I'd be interested in. So for instance, let's say I'm interested in knowing the probability of flipping 2 tails. When I flip a coin 3 times, then R would equal to 2. N is the number of trials in total. So still sticking to that coin toss example, N would be 3 if I flip a coin 3 times. And P is the probability of a success. And Q is the probability of a failure, which is the complement of a success. So that's equal to 1 minus P. Now let's go ahead and look at a quick example of how we may use this. Okay, we're given an example in which we're told that a biased coin is such that the probability of obtaining tails is P equal to 0.3. We're then told that the coin is flipped 3 times, and we're asked what is the probability of obtaining exactly 2 tails. Okay, now we're going to do this in 2 ways. The first way will be to use a tree diagram, and we'll find the answer to this problem. Then we'll use the binomial distribution to highlight how the binomial distribution allows us to obtain the same results as we would with a tree diagram, but without needing to draw it. So let's get started. With a tree diagram, on the first flip of a coin that is, we'd either get heads or tails. And remember, this coin is biased, so the probability of obtaining heads is 0.7, and tails would be 0.3. On the second flip, we'd either get heads or tails again, with the same probabilities. (0.7 and 0.3). And same thing on the third flip. We'd either get heads or tails, heads or tails. 0.7 and 0.3, 0.7, 0.3, and finally heads or tails, 0.7 and 0.3. And there we go. Now in the question, we're asked to find the probability of obtaining exactly 2 tails. Now this term exactly is important. It means it has to be 2 tails. It can't be 3. So looking at the far right-hand side of this tree diagram, we need to look at all the possible outcomes of this experiment in which there are exactly 2 tails. So with just walking along the branches, we can figure that out, going from left to right. And we quickly see that one of the possible outcomes is heads, tails, tails. That one definitely has exactly 2 tails. Another one would be tails, heads, tails. And another one would be tails, tails, heads. And those are the only 3 outcomes with exactly 2 tails. Now, the probabilities for each of those can be written on the far right-hand side. So let's see, for the top one here, the probability of heads and tails equals to the product of all the probabilities that we encounter going from the far left to the end of that path. So that would be 0.7 times 0.3 times 0.3. And with a calculator, we find that that's equal to 0.063. Similarly, for the next possibility, we have tails, heads, tails. So that's probability of tails and heads and tails. And in this case, the probability would be 0.3 times 0.7 times 0.3. And again, with the calculator, we find that's equal to 0.063. Finally, the last possible route would be tails, tails, heads. So that's the probability of tails and heads, which equals to 0.3 times 0.3 times 0.7. And once again, that's equal to 0.063. Now, all 3 of these outcomes are mutually exclusive, and all 3 of these outcomes correspond to exactly 2 tails. So the probability of either one of these occurring is simply the sum of the 3 probabilities. And so we just have to add all 3 of these probabilities up to find the probability of obtaining exactly 2 tails. So I'll just write this here, probability, and I'll just write exact for short, 2 tails, equals to the sum, so that's 0.063 plus 0.063 plus 0.063. And we find that's equal to 0.189. And there we go. The probability of obtaining exactly 2 tails is 0.189. Done. Now that's how we would do it with a tree diagram. But we can also do this with the binomial distribution formula. And let's just remind ourselves of its formula. So we have probability of capital X being equal to R equals to the binomial coefficient nr times p to the power of r times q to the power of n minus r. Now let's define each of those things there. So capital X, in this experiment, we're interested in obtaining tails on this experiment. So we're going to go ahead and define capital X as being the number of tails obtained. And that's obtained in this experiment. So let's see, if I flip a coin 3 times, well, I can either get no tails at all, so that's 0, 1 tail, 2 tails, or 3 tails. So X has to be either 0, 1, 2, or 3. Okay, we're flipping the coin 3 times, so n, number of trials, is equal to 3. We're interested in the probability of obtaining exactly 2 tails, so the number of successes we're interested in, is 2, so R is equal to 2. The probability of a win is P is equal to 0.3. That's the probability of obtaining tails. And the probability of a loss, that's Q, is equal to 1 minus P, so that's equal to 0.7. And so now, all we have to do is replace all these values inside our formula. So that's probability of X being equal to 2 is equal to, so 3, 2 as a binomial coefficient, times 0.3 to the power of 2 times 0.7 to the power of 3 minus 2, so that's just to the power of 1. And now, with a calculator or not, up to you, we find that the binomial coefficient 3, 2 is equal to 3. So that's 3 times 0.3 squared times 0.7. And we find that that's equal to 0.189. In other words, we find exactly the same result as we had done with our tree diagram. Now, a very important thing to notice here is the binomial coefficient, 3, 2, gave us the value 3. Now, this value 3 tells us how many outcomes on our tree diagrams correspond to the outcome we're looking for. In other words, thanks to this formula, we no longer have to draw this tree diagram. The result is exactly the same, but that binomial coefficient is telling us how many branches there are which correspond to our outcome. That's that binomial coefficient's job. And so that's how the binomial distribution formula works. In essence, it's just a shortcut to tree diagrams. Let's look at one more example. In this case, we're still working with the same bias coin, which has a probability of 0.3 to land on tails. But this time, the coin is flipped 5 times. And we're asked the same question, what is the probability of obtaining exactly 2 tails? Now, the fact that we're flipping the coin 5 times really suggests there's no way we're going to draw a tree diagram for this. We could, of course, but that would take a lot of time. And it would be worse if, say, we flipped the coin, I don't know, 20 times, 30 times, or 40 times. And that really is where the binomial distribution formula becomes useful. So to solve this, let's just go right ahead and say, okay, well, we're interested in the number of tails we obtain. So we're going to define our discrete random variable x as being the number of tails. And because we're flipping the coin 5 times here, x could be 0, 1, 2, 3, 4, or 5. Now let's just remind ourselves of the formula. Okay, we have probability of capital X being equal to R. R is the number of successes we're interested in. So in this case, we're interested in obtaining exactly 2 tails. So R is equal to 2. And let's see, number of trials n. N is equal to 5 because we're flipping the coin 5 times. The probability of a success or win is the probability of flipping tails, so that would be 0.3. So P is equal to 0.3. And the probability of a failure or a loss is Q. And so Q is equal to 1 minus P. That's equal to 1 minus 0.3, which is 0.7. And now we're set. We have everything we need. We can go right ahead and calculate. So the probability of the number of tails being equal to 2 is equal to 5, that's 5 flips, 2, number of successes, times p to the power of 2, times q to the power of 5 minus 2, so that's 3. That leads us to 5, 2, binomial coefficient, times 0.3 squared, times 0.7 cubed. And now with the calculator or not, we find that the binomial coefficient 5, 2 is equal to 10. So this whole thing is 10 times 0.3 squared times 0.7 cubed. And now, let's just stop for a second. What this means is, if we were to draw the tree diagram, there would be 10 branches we'd have to add together, 10 probabilities to find. And that's 10 branches with only 2 tails. Imagine how many branches there would be in total. Well, in fact, it would be 2 to the power of 5. That's a lot of branches. So the binomial distribution formula is definitely better. And we find, with the calculator, the probability of the number of tails being equal to 2 is equal to 0.3087, which, if we round to 3 significant figures, would be 0.309. And there we have it. That's how we can use the binomial distribution formula.